Okay, this is the second, listen up. This is the second equilibrium chapter. The first one was Kc we were solving for. That was the concentrations. And Kp, that was the pressures. We basically solved for the equilibrium for a reaction. Guess what we're going to be solving for here? Acid and base reactions. Now, I need to spend today doing some review. All right, almost everything we're doing today, actually everything we do today, will be something you either saw in your notes back in Chem 1, and I'm just going to refresh you on it. All right. Now, because of that, I typed all this out for you so you don't have to rewrite all this. At the time, I was writing all this for you and teaching it to you. What makes something an acid and what makes something a base is the first thing you have to know how to do. Arrhenius versus, what was the other one? Do you remember what being up there? Bronsted. Arrhenius and Bronsted acids and bases. Now listen, what makes something an Arrhenius acid is he has to have these things. What are they? Hydronium ions. Got to have hydronium ions, H3O plus ions. Like in the case of this reaction right here, right? Now he's forming those hydronium ions by also acting in this case as a Bronsted acid, but you don't know that yet. Well, all we care about is anything that forms these guys makes them an acid. Anything that forms these guys makes them a base. The problem is, in order to have an acid or a base, you got to have water around. You got to have water for him to react with, or you got to have water for the sodium hydroxide to break up into. So if you don't have water, does that mean you can't have an acid or a base? No. Turns out you can have Bronsted. By the way, I'm going through these quickly, but we are going to practice these. The last back page, we're going to work on some practice ones together. Bronsted acid and base definition says you got to donate an H or you got to accept an H. Look what happens in this guy. See what's happening here? HCl plus NH3. There's no water around. Matter of fact, I did this demo, if you remember. I did this demo. We had a glass tube with two cotton things soaked, one with hydrochloric acid, one with ammonia. There was no water, but it formed a cloud in the middle, if you remember that. All right. So in this case, this hydrochloric acid becomes just Cl. So he lost an H. He's the Bronsted acid. The NH3 becomes NH4. He gained an H. And by the way, why is an H a proton? Why is it the same thing as a proton? Because how many protons are in hydrogen? How many electrons are in hydrogen normally? One. So if he loses an electron, all right, kind of like this. Like, look, I'm going to do a little bit more of the electron dot here in a second. You realize when an HCl, here's his electrons. When he leaves and goes over there, he does not take that electron with him. So what's left behind here, why is chlorine now has 8 electrons? He's got a -1 charge. So all you're adding, all he's going is just basically a proton. Just one proton. The electron is gone. He's still there. Okay? So I'm going to ask you to tell me each of those, but there's a problem. We did not learn back in Chem 1 about Lewis acids and bases. All right? Never taught you about that. Now, actually, I made this up. One of the reasons I'm changing this is that I realized in the last few years, the new regulations, since they redid the AP test again, is they are basically not testing on Lewis acids, from what I understand. But I'm going to give it to you anyway, just because I want you to understand that you will see it in college. If you take a chemistry class in college, there's a good chance that the professor you might get would want you to know what Lewis acids are. And they're not that hard. Won't take me very long. An acid, according to Lewis, look at the difference. A Lewis acid accepts an electron pair. Acid, according to Bronsted, donated a hydrogen, kind of like the opposite, right? A base, according to Lewis, donates an electron pair, all right? Kind of like the opposite of accepting a proton, all right? So you can have an acid and a base without water. You can even have an acid and a base without a proton transfer. You can have an acid or a base by just transferring an electron pair. All right, and I have a little example of that for you here. You'd be hard-pressed if I just gave you that example to figure out, oh, yeah, I could see which one's the acid or base there. But if you drew out the electron dot notation, like I'm going to show you, like it's drawn for you here, you'll see that the carbon atom is actually accepting electrons from the water. I'm going to draw another example of this in a few minutes when we practice these. Okay. So if he's accepting, like carbon accepts an electron pair, he is considered, if he's accepting an electron pair, that's the opposite. Sorry, I'm backwards. If he's accepting an electron pair, that makes him an acid. If he's donating an electron pair, it makes him a base. All right. Now, the last two things, oh, actually, not the last two things. The last two things before I do some examples that you also saw in Chem 1 are these two words. And sometimes, it's going to happen in the AP test, I'm sure. You're not going to know something, but you can figure it out. Have you heard amph in front of something before. Amphibian. What do you think amphoteric, even if you don't remember it from 2 years ago, what do you think amphoteric probably means when concerning an acid or a base? It can be both, exactly. Remember, amphibian live on both land and water. Amphoteric can be either an acid or a base. And all this is written, you don't have to write it in there. Like, for example, take a look, not at the same time, by the way. Can't be at the same time. HCl plus water, what is acid acting like in this problem? What is the HCl acting like in this problem? An acid. What is the water acting like in this problem? A base. He accepted an H. But watch water in this problem. Come on. Here we go. All right. Look at water in this problem. Yeah. Water in this problem goes from H2O to just OH. What did he do? He donated. So here, water was an acid. Here, water was accepted. Went from H2O to H3O. Water was a base. Now, this is going to get particularly confusing when I start to try to classify each guy as an Arrhenius, Bronsted, or Lewis acid or base. So that's what I'm going to get to in just a second. But one last thing is about conjugate acid-base pairs. I very briefly mentioned them in Chem 1, and there's a good reason for that. In Chem 1, almost all of our, not almost, except for this one part of notes, every reaction you saw in Chem 1 had an arrow going one way. We did not talk about equilibrium reactions, at least not chemical ones, just phase equilibrium. So for the conjugate acid-base pairs, you have to assume you don't just have a one-way, you can go both ways. So this guy can get together with him and make these two, like we now know happens all the time in equilibrium problems, or these two guys can go back that way. And by the way, on your paper, I think I didn't have this graphic, so make sure you have a double arrow on that one. I didn't have it when I made up the paper. Okay? All right. Here's my statement about this. You can all answer me the question about in the forward direction. H2SO4 is becoming just HSO4. He must be the acid. He donated an H. This guy gained one. He must be the base. But all a conjugate acid is saying, what would he be in the reverse direction? In other words, after that H2SO4 loses an H, going backwards, what is he acting like? If you look at it backwards, what's he acting like? He's acting like a base on the way back. So an acid forms a conjugate base, and a base forms a conjugate acid. And here's the deal we're going to get to. We're going to be able to tell with numbers. The thing is, in general, the stronger the acid, the weaker its conjugate base. And that makes sense, because we know that a strong acid would mean somebody who wants to break up, wants to give up an H. Once he gives it up, he won't want to get it back very much, right? So that's why a guy who's a really good acid is a really weak conjugate base. And a guy who's a really good base would be a really weak conjugate acid. He doesn't want to get back what he just gave up, or vice versa. He doesn't want to give up what he just got. Okay? So that makes sense, hopefully, about that, but it's going to become a lot more clear when we do actual calculations with acids and bases that are weak acids and weak bases. All right, so that guy's the acid, that guy's the base. That guy will be the conjugate acid. He came from the base. The conjugate base came from the acid. All right, good enough. Now, time for some practice of these because it's been a while. All right, so you all have these written on your paper. Let's go through them. Can you tell me what water is in this first case? Is he a Bronsted or Arrhenius acid? I'm going to stick with just Bronsted Arrhenius until the last one. He's an acid is correct, but is he a Bronsted acid or is he an Arrhenius acid? Well, he's definitely donating. Everybody can see that. So that makes him a Bronsted acid, right? Okay. What is ammonia then? NH3 is gaining one, so he must be a Bronsted base. Here comes the mistake. Do we also have an Arrhenius something? Yeah, what do we have? An Arrhenius what? Base. Two mistakes. One, there's my Arrhenius base. He is not an Arrhenius base. OH is the ionized form when somebody was acting as an Arrhenius base. So the second mistake is, which of these two is the Arrhenius base? What do you think? Think of the definition of Arrhenius. Arrhenius is something when you add it to water.
Oh, no.
Listen again. Something when you add it to water forms hydronium or hydroxide ions. Now, water can never be the answer, can it? It's something that you add to water. Also, here's another reason why this guy must be the Arrhenius base. If I put down him as a base, what did I just say? You can't act like an acid and a base at the exact same time. So I would have this guy being an acid and a base at the same time. Not possible. Okay? So that is the way you do this one. Let's try this one on your own, and I'll do it in a second. Try this guy. All right. Matter of fact, I'll put all of them up because you're going to be going to all of them in a second anyway. I recommend doing the Bronsted first. Everybody probably agreed that this guy's the Bronsted acid, right? And therefore, this guy's a Bronsted base. Do we have an Arrhenius anything in this case? No, we're done. Sometimes you have just Arrhenius, I'm sorry, just Bronsted or just Arrhenius, and sometimes you have both. Okay? How about this guy? Everybody agree this guy is the Bronsted acid. This guy would be the Bronsted base. I am kind of probably should redo these because if you notice, I've got the acid on the left side for every single one of these. So it gets to the point where you start to expect the first guy to be the acid. Don't. It could be in any order. I got hydronium ions formed, which means I've got an Arrhenius acid as well. Who's the Arrhenius acid? HCl. Good. All right. This guy, by the way, I don't have it here, but he should have water. He's dissolving in water. Okay. It's like and we're going to get to solubility as well, equilibrium problems as well. He dissolves in water and gives me OH ions. What does that make him? An Arrhenius base. Is he also a Bronsted anything? No, he's not. And finally, you got this guy down here.
If it's by itself, it doesn't have Bronsted.
When he's by himself?
Like when he's decomposing.
What about it?
Breaking up.
Yeah.
There's only one.
Okay.
Bronsted acid base, because there's only one of them.
Well, that's pretty much logical. If there's only one guy, he can't be donating now. So he can't be a Bronsted anything. That's true. All right. If you look at this guy down here, again, I'm not going to ask you to do any of these on the test or in the AP exam, but real quickly, I possibly can show you why this guy works. And you can tell he is a Lewis. This is probably a very good illustration of this. It's kind of hard to do with this new board, which I don't like, as you all know. But basically, that's how you would draw boron. And you should draw this beneath it, by the way. Draw that guy. You would have drawn him like that. I'm drawing him quick, but the fact is you would have drawn him like that based on what you know about how to draw electron dot notations. You know, needed, available, shared, all that kind of stuff. Boron is one of those exceptions, remember? There aren't many. There are a handful of people. Hydrogen's an exception. Boron's an exception. They're really the only two you're most likely to run into, but there are a couple others I wrote down in your notes. He's an exception in that he doesn't need an octet. If you were to do the needed, available, shared, boron has only 3 electrons. Okay, that's how many he has. But he only wants 6. He doesn't want 8. So he's happy like that. Now, a fluoride ion looks like this. You all agree? Fluoride ion has to look like that. He has 7 electrons plus 1 extra. That's what gives him the -1 charge, or 1 negative. When I redraw this guy as BF4, I think it's pretty obvious what happened. And I could just draw dashes here, but I'm going to draw out the electron dots just to show you what happened. That's as good as I could do with this board. I like the old board better, as you all know. Look what happened. Didn't this guy basically donate that electron pair to the boron? The boron didn't have an electron pair up there. Now he does. So that's what makes him a what? Look back at your notes, because you just got that. It's kind of you always think of it as the opposite of Bronsted. Bronsted, if you're donating a proton, you're an acid. So what are you probably doing if you're an acid for Lewis? You're accepting an electron, right? So what is fluorine in this guy? He's donating an electron, which makes him a what? Right, makes him a base. Okay. All right, good enough. Now, I left it there. That's why I'm recording this, because I realized when I gave you the homework tonight, there's a couple of things I didn't tell you about. They are easy. I did talk about it once before under ester reactions. You may remember it there. Let me show you. Oh, by the way, that homework, let me just go back for a second to the homework for those people who are watching the video. Real quick, you can freeze it if you need to, but you guys have it over there, so you don't have to write it down. All right. Everybody should know from the ester reactions when I reviewed this then. What am I going to get from this? HCl plus NaOH. Salt water. NaCl plus HOH, or H2O. I even made a nice color. See? You take the positive ion from the base, the negative ion from the acid, you put them together, you make a salt. Okay? And you always get water. So that's basically we saw that. We saw that once before. Here's what I forgot to tell you in the previous recording, and I did catch up in the morning. I realized I should do this, but I didn't give it to him. If I give you specific examples, it can get a little hairy. Watch. What happens if I give you H2SO4 plus, and I know there's no room for this on there, okay? It's okay that there's not. I'm about to give you a sheet that has it on here, right here. Okay, this sheet here, I just redid today. That's one of the reasons I don't have your test done. I redid this whole thing here. It looks like your old common ion sheet, but I added a lot of other information. You're going to need this to answer these questions. H2SO4 plus AlOH3. Now I got a problem. Okay, I got to worry about a lot of things in this. Not the least of which is how to name all these guys. Do you remember how to name these guys? No. I'm going to give you the chart. It's there on the sheet. We'll go over it. Also, what else? This is part that you should be able to do. Can you balance them correctly with the right charges? The salt's always going to be the positive ion from the base, Al, and the negative ion from the acid, SO4. But I can't just leave it as AlSO4, can I? I got to use a 3 plus here, a 2 minus here, 2 there, 3 there. And I know I'm going to get this from somebody. Well, at least these in Chem 1. H2OH3. That's what I'll get. Is that the formula for H2O for water? No, it's H2O. But you do have to balance it, right? Got to balance this guy. How are you going to balance him? What will you need? Anybody? I got 3 sulfates here, right? So I'll need a 3 in front of there. I got 2 aluminums there. I'll need a 2 in front of there. And how many total waters do I now need? Well, 3 times 2 is 6 H's there. 2 times 3 is 6 more over there. So I need a total of 12 H's. So I'll put a 6 in front of that. Okay? So now you got to name everybody. This guy happens to be called sulfuric acid. But what if it was H2SO3? What would it be called? Sulfurous acid. This guy's called what? AlOH3 should be easy. Aluminum hydroxide. What's this guy called? Aluminum. It's not sulfide. Sulfate. And if it was SO3, it would be sulfite. If it was SO2, it would be hyposulfite. If it was SO5, it would be per, not hyper, just per. Yeah. So you notice where I'm going here with this. I'm going with the fact that we got to know that. Don't copy it down. I wrote it down for you on this paper. You're going to need that to be able to answer 50 and 52, all right, which are also on this test. Okay? Now, that's good enough.